Hello everyone, welcome to the beginning of chapter 16, and this is the chapter hopefully we've been waiting for. Just a short chapter for one, and also just a lot of review, okay? A lot of things that hopefully we've touched on over and over again. So sensation, concept, overall general idea of sensation, and then sensory receptors. And this chapter is really split mostly into sensation and motor. And we're going to work on what's happening as you sense things, and then moving up those sensory ascending pathways up through the thalamus into the cortex. We'll go over all that. Then we'll deal with the motor response, and we'll just overview. And you've seen so much of this, so I'm really hoping that this is a great chapter for you to really feel good about the work you've put in and just get a lot of review. So first four, 1 through 4 in the upper left, that's just a really overall, very generic overlay of 4 concepts in order: stimulation, transduction, sensation, and perception. And then there's some physiological processes A through D, and we'll match them up to give you a sense of how we look at sensation. Everything from the wind blowing to you knowing the wind is blowing in that pathway, right? And then 5 through 19 are just a series of different sensations, really specific sensations, and we'll categorize those twice. First, we'll categorize them as general somatic, general visceral, or special. Then we'll characterize them as whether they're being handled by each of those 6 H through M specific types of receptors: chemical, nocial, pain, thermo, osmolarity, all that types of receptors. Okay, let's cover that first overview between the wind blowing and you saying, oh, the wind is blowing, and knowing that the wind is blowing, knowing which way the wind is blowing, right? It's going to start off with the physical stimulation, some physical thing in the world, a light ray, a photon, the wind blowing, sound waves being compressed when a tree falls in a forest and sound being pulsed at you. Some sort of physical stimulation. A breeze pushes on the hair shaft, the pili, on your integumentary system. You have to transduce that. Transduce, move across. You got to get it from a physical stimulation, a sound wave, a light ray, a physical force, a wind, air pressure, something like that. You got to turn that into depolarization of positive ions, sodium and calcium for the most part, into through a membrane into a specific cell. So that's transduction, changing the type of energy from one form to another. What happens when the wind blows on those pili on your integumentary system? You hopefully have a mechanoreceptor that bends to open under the pressure of that breeze, physically is pushed, and that allows an ion channel to open up, and sodium, which is calcium, which are always higher outside the cell than inside, to flow in. You could also lose chloride out in other instances too. You could lose negative charge out of the cell. Regardless, the sum story, and with sensation, it's almost always positive charge going into the cell. You depolarize the sensory receptor, right? The cell potential changes. If it reaches threshold, again, go back to the videos on action potential. If it reaches threshold, if it goes from -70 up to -55, boom, action potential triggered. You are now sensing that. Action potential running into the central nervous system. You're now sensing that because there's electronic activity in the CNS that is actually real. Whether you perceive that or not depends on whether it stays on a lower loop in the CNS, or if you perceive it, it's sent on an ascending pathway up to the cortex, where you move it to an association area, first to a sensory area. So first it'll go to the primary auditory or the primary gustatory area or the primary somatosensory area. That's all part of sensation. But once you move that over to the association area and you compare it with what you've sensed previously, and you go, aha, that is so-and-so, and you name that taste, or you name that smell, or you name that tune, now you have perceived it, and that's the end of the road. Okay? So that's just that overview. And then let's break the senses up. You have 2 types, general and special. The special, I'll do the special first. Why not? They're on the right. Taste, smell, vision, hearing, and equilibrium, right? Those are the special senses. That's next chapter, chapter 17. We'll really dive into those. On the general side, which is just the rest of the body, it's not special, you have somatic, meaning all of your body, sort of your external, your integumentary system, and all of your proprioceptors, kinesthetic receptors, muscle spindles, tendon organs, all those things. And you're picking up all of that happy and crappy, the light touch, light pressure, vibration, proprioception, pain, itch, temperature, all that. And you also have your visceral that are coming from your internal organs. Remember which two? was stretch and chemical, right? Your interoceptors, picking up stretch of the blood vessel walls, stretch of the intestinal walls, and then your chemistry too, picking up all the chemistry in the lumen of those organs too. Okay, that's how we break it down. And if you ever see something you come across in some sort of neuroanatomy, neurobiology, somebody say, well, that's clearly a GSE fiber. Okay, well, don't panic, because look, we got the G covered right there, and oh, look, we got the S covered. And we know the E's efferent, right? So, okay, what do you got? You got an efferent signal being sent to general somatic, right? Or more specific to this module, let's say somebody says it's a GVA fiber, because this is a sensory. So we know it's afferent, so we know it's sensory. Okay, we got the G covered, and we got the V covered. It's a general visceral afferent fiber. What does that mean? Well, it means that it's a signal from the gut that we're stretching out, being sent along afferently from the viscera as part of the general sensus. So that would be a GVA fiber. If you ever come across that, you won't panic. You'll just parse it down like that. Okay, lots of ways to overlay and organize. The next few slides are purely organizational. 3 different ways to organize sensory information. You can do it by the type of receptor. We are way out at the absolute terminal or distal end of the nervous path, where the rubber meets the road, where you are right out there external. These are external receptors that are able to, they're in a position, they are right on the integument or in the muscles. They're able to pick up the physical world, and they're able to interact with the physical world. They come in 3 types. We know this. One type is free nerve endings, right? We talked about this in the integumentary system. They're just the dendrites, and they're just exposed inside the dermis or the epidermis, or inside of a tendon organ, something like that, or inside a muscle spindle, a proprioceptive organ, and they're just dispersed. And they're really good for chemoreceptors and nociceptors, right? Free chemicals that just cruise through and they bump into these nerve endings. If it's an odorant molecule or a taste molecule or some sort of nociochemical, some sort of pain chemical, a bee venom, something like that, then they're going to bind with the receptors on the dendrites and the cell bodies of the receptor. In this case, the dendrite, because the cell bodies are all over here. Right, so everything from the receptor on down the line is the same. These are pseudo-unipolar. You got your axon, you got your terminal at the end, no problem there. But it's really at the beginning that it's really going to differ. And the free nerve endings are there, and they're good for chemoreception, and they're good for nocioception, right? And they're good for thermoreception, because there's special proteins in there that can sense temperature too. All right, let's move down to an encapsulated ending. So you've got the nerve ending inside, but now you've wrapped it in a connective tissue capsule. What are these good for? Well, these are good for physical pressure. Any kind of physical pressure stimulus, so transducing physical pressure. So Pacinian, Meissner's corpuscles, right? Physical pressure is going to get this capsule at the end to bend. It'll just push that capsule. And when it pushes on that capsule, these free nerve endings inside, channels will open up, and you'll get depolarization in there, and you'll beam on down the line, right? And by the way, these two, this sort of initial depolarization that would happen either via a ligand-gated channel, right, or a mechanoreceptor here, so a chemoreceptor at the top, or a nocioceptor or thermoreceptor, or a mechanoreceptor in the middle here, they would create a generator potential. And that's that initial EPSP that triggers an action potential that gets sent down the line saying, hey, sense, this is what we just sensed, okay? Compare that to the third, which is a highly specialized, only in the special senses. So the top 2 are somatic or general. It can be visceral too. The top two are general. Okay, somatic or visceral. The bottom is special, and it's these special receptors, and it's a 2-part series. If you look, this is all not one neuron. Excuse me. You got a special receptor. Usually, in this case, if it's going to be gustatory or olfaction, it's going to be a chemoreceptor. If it's going to be the special sense, it's going to be mechano. But anyway, the chemoreceptor here is going to do a two-part. It's going to receive and generate a receptor potential, a little different than a generator potential. And you're going to have an individual separate step here of release across the synaptic cleft here, and a separate step. And then the receptor that we know of is a 2-part, and then the receptor is going to pick that up, and it's going to move it on down. So two-part step, which is a little slower, right? But you wouldn't expect odorant and taste and olfaction to have to be super fast responses, right? Screech of brakes and diving for your life, or feeling somebody stab you. Those are kind of important things to know immediately with incredible rapidity, right? But taste and olfaction a little slower because it's sort of two-step process, but no big deal. All right, those are the three types of sort of terminal endings that sense. Let's organize by another way. Let's organize by three different locations or types of receptor. The exteroceptors are the ones we talk. They're in the integumentary system. They're all these right here. We'll go to the next module. We'll cover these in detail, right? They're the free nerve endings in the dermis and the epidermis, and they're the tactile receptors and the mycers and the Pacinian and the dermis, right? And all those sorts of things. Whoops, didn't mean to do that. All those sorts of things, okay? External, exteroreceptors, interacting with the outside world. Or if we come inside, we could also have interoceptors, and we know these are very important in the ANS, right? So sort of in general, external receptors and your somatic nervous system, SNS, these interoceptors are really good in your autonomic nervous system. And where would they be? Well, in the lumen of the gut, you'd have a little chemoreceptor right here, or a little stretch receptor right here, and it would be picking up chemoreceptor there, maybe a stretch receptor here inside of the submucosal plexus, and you'd be picking those up, and you could do either the ENS if you wanted to, all within the ENS, or you could of course just beam it right up to the central nervous system too if you want. And go back and watch the video on the enteric nervous system if you're unsure of these sort of pathways and how they interact. But anyway, it's internal, it's visceral. Interoceptors are also called visceroceptors, right? Receptors of the viscera. No big deal there. Piece of cake to understand. And lastly, proprioceptors. And we have those three types. So we'll go into these again in the next module in more detail. They are here for you to see. They are the muscle spindle, these sort of nerve endings right in the middle of the intrafusal fibers. They are the tendon organs in the tendon, and they are the joint kinesthetic receptors. And I think I have that on this next slide. I love this slide, right? It's these little receptors on this athlete, on the shoulder, on the glenohumeral joint, on the elbow joint, right? Picking up on the occipital atlanto-occipital joint, right? Picking up, that's a little higher, but you get the idea. The atlanto-occipital will be quite a bit higher. But anyway, picking up motion, picking up rotation, picking up acceleration, all those things that joint kinesthetic receptors do embedded in the fibers in the articular capsule of your joints, right? And here externally on this athlete, but you get the idea. They're picking up all this great motion, acceleration, deceleration at the joints, as well as position of the joints too. Okay, and then lastly, we can separate out the sensory information according to what type of receptor is picking it up. And this slide, I just a couple random slides for examples. This slide is trying to cue you into how a chemoreceptor works. And an odorant molecule is going to come right in and bind onto this protein, and it's going to trigger this whole effect. And what it's going to end up eventually doing on this protein over here is opening up the sodium channel and allowing for depolarization. So you're transducing the stimulus of an odorant molecule floating through space. You're transducing that to ion and depolarization and change in the membrane potential and signaling that you picked up this specific odorant molecule. And do you remember this little pathway here? Do you remember, go way back to the beginning of this course in 40B, go back to sort of that anatomy of the neuron, and then pick up that difference when we talk about ligand-gated channels. Pick up that difference between ionotropic and metabolotropic. Remember that? Well, this one, of course, would be which of the two? It'd be metabolotropic, right? Because you're picking up on, you're binding on one integral membrane protein, but then you're affecting transduction and ion transport on a separate, and they're coupled together by this very common G protein, adenylate cyclase, cyclic AMP, this whole process. If the binding and the channeling were all done on the same protein, remember that would be ionotropic. Right? So just a piece of review right there. No big deal. And let's just move to another one. This would be a very good example of a mechanoreceptor. And this is inside the inner ear, and you've got fluid and a wave through the fluid, literally like a wave through the ocean here, coming around the corner and coming around. And as this wave comes, it pushes up on this little whole apparatus here, and you got these little tiny hair cells that are embedded in this sort of membranous substance here. And as this thing waves and shakes, these little hair cells get woven, and they're kind of being pushed because they're stuck inside this membrane. They're being deflected. Those little hairs are being deflected to the side. And that's a mechanoreception. That's how you pick up sound. That's how you pick up equilibrium too. And those are mechanoreceptors because those little hairs are being pushed and deflected. And maybe here the channels are closed, but maybe there the channels open up. And then what happens? The channels open up, and then boom, back to channels closed. And then some other wave comes along and deflects, channels open, boom, channel's closed. Something like that for a mechanoreceptor, right? And then I think lastly, or close to lastly, let's talk about sensory adaptation, because all these receptors, whether they be chemical, osmoreceptors, photoreceptors, whether they be external, internal, or proprioceptors, whether they be free nerve endings or encapsulated or sensory receptors, whatever they are, they're going to adapt at a specific rate. And adaptation means tuning out. Adaptation, if you're very fast to adapt, you just simply tune out. You get a signal, you say, okay, got it, sent it, and then if that signal persists, you just shut it down and you stop relaying that information. It's just not that important. So, okay, you know what? I told you once, I'm not telling you again, okay? And look at the Pacinian corpuscle, right? This is sort of the number of frequency of stimuli per second or some such like that. The Pacinian corpuscle, within 1/10 of a second, it's done telling you, even if you can, remember, Pacinian corpuscle is deep pressure. So you push kind of hard on the integumentary system, and that Pacinian corpuscle is saying, okay, I'm being pushed against, sending a signal. Keep the pressure there. I'm pushing against my forearm here, right? Keep the pressure there. That first signal gets sent. Sure, somebody's pushing against our integumentary, but within 1/10 of a second, even though you continue to push, nothing else gets sent. It's like, I'm done with that. Not important. Pushed once, got it, not telling you about it again, okay? Hair receptor, the hair root plexus, or the paratracheal receptors, also really fast to adapt. What are really slow to adapt? A joint capsule receptor and a muscle spindle. And that's important because you are constantly, that means they're constantly talking. Hey, here's where I am. Oh, hey, here's where I am now. The elbow, a receptor in the elbow. Oh, now I'm here. Now I'm here. Oh, now I'm here. Now I'm here. Now I'm still here. Now I'm still here. Now I'm still here. At what point is it not a good idea to know where your body is in space? That could be, we have just outrageously courageous people who defend our country in the military, first responders. It could be a matter of life or death in certain situations for these people to know exactly where their body is in space, right? So it's just always a good idea to always know where your body's in space. So proprioceptors are an example of an incredibly slow adapting receptor, and they just keep telling you what's going on no matter what. Chemoreceptors do the same. When is it a bad idea not to know your blood chemistry? I would like to be keeping track of my blood chemistry 24/7, and fortunately for me and for you, your autonomic nervous system does that without you even knowing. Okay, nociceptors, pain. It's really, really stressful, and it's really annoying and frustrating. But pain is critical to keeping us alive. So we're constantly being told this hurts. Oh, yep, still hurts. Yep, still hurts. Still hurts. All right, you get a bang, you get a bruise. That physical pressure is gone days ago, weeks ago, and you still, yep, still hurts. Yep, still hurts. Still hurts, right? Frustrating, but it kind of helps to keep you alive, right? Pain is a very critical element there. Okay, so just be comfortable with between slow adaptation and fast adaptation. In another module, next one, when we go into all the receptors in detail, we'll talk about specifically which ones Pacinian are really fast adapting and which ones are really slow adapting. Okay, these four, let's crank these out. These first four right here. Stimulation is going to be C, some sort of physical process, binding odorant, deflection of the pili via change in air pressure, a breeze. Light, striking a photoreceptor. It's almost like you don't do anything. You just stand there, let these things happen to you, let you be stimulated by the environment, right? Then we need to transduce. How are we going to do that? Well, we're going to depolarize something, right? We're going to take the distal part of a membrane, either via free nerve ending or via an encapsulated or capsule, if you will, a connective tissue capsule, or there's a special sensory receptor. And we're going to open up a channel. We're going to get ion flow. So we're going to transduce. We're going to change physical stimulus to ion flow inside of a nervous neuron or a nervous cell, nervous tissue cell or a neuron. Sensation, that's going to be getting you into the CNS, right? Action potential sent into the CNS. Now it's on record. I sense this somewhere in my lower CNS. You want to perceive it? We'll move it all the way up to the big boys, all the way up to the cerebral cortex. Relay it through the thalamus, bring it up to some sort of primary area, primary visual, primary auditory, primary olfactory, primary gustatory, primary somatosensory, and then bring it over to the association area, scroll through, oh, yep, that is sushi, or that is a green car driving fast down the road, right? You've just identified and you've processed and you've perceived at a cortical area or a cortical level. You've perceived it. Okay? Now, we're going to blow through these twice. Once for E, F, and G, and then once again for H through M. So vibration is, of course, a general somatic. Hearing is a special sense. Equilibrium is a special sense, both carried by the same nerve, both part of the inner ear, right? Pain is a general somatic, but also you can pick up pain in the viscera, right? Absolutely, you can pick up pain in the viscera, right? Heart pain is one thing you really want to pick up. Intestinal pain, colonic pain, right? Stomach pain, those are all things that you want to pick up. Itch is general somatic. Stretch can be general somatic. You've got very special receptors that pick up stretch in the skin, but of course, one of the two biggies that the viscera receptors or the interoceptors are picking up is, of course, stretch of the viscera. Right? Light touch and pressure, general somatic, piece of cake. Sight, special. Crude pressure, general somatic. Chemical makeup, general visceral, right? That's one of the two things you want to know, the chemical makeup of the viscera. I guess I'll put, I'm going to put, no, I'll just leave it there. I was going to put E for general somatic because nociception is really identifying chemical makeup, but I'll leave it to just general visceral, and I'll do pain. We already did pain on the general somatic, okay? Proprioception is general somatic, of course. Gustation is a special sense. Temperature is going to be a general somatic. Olfaction is a special sense. And blood osmolarity is a general visceral, right? Your blood flows through your body, but it's picked up within the viscera, within the carotid arches and things like that. It's generally considered to be general visceral because it's controlled by cranial nerves that are involved in the autonomic nervous system. Okay, good there. Freeze, take a shot, take a screenshot, pause, lock this in because I'm getting rid of it, and we're going to overlay H through M. So vibration is a mechanoreceptor. Hearing also accomplished by a mechanoreceptor. Equilibrium also accomplished by a mechanoreceptor. Pain by a nociceptor. Noci is a root for pain. Very special receptors in free nerve endings that pick up just pain. Pick up the venom and the toxin. If prostaglandins and bradykinins that you release to indicate an area of pain, you just got smashed on the arm, you release those chemicals. But foreign substances, bee venom being a very important one or a key one, coming in and signaling, hitting, just smashing those nociceptors, saying ow, ow, ow. Itch, where am I? Itch is going to be, I'm going to put it as a kind of a low-grade nociceptor, really. Itch is like a low-grade pain, right? Stretch is a mechanoreceptor, right? Distending that receptor and bending it to get depolarization. Light touch of pressure, mechanoreceptor. Sight, photoreceptors, very special photoreceptors that transduce light rays into depolarization and stimulation. Crude pressure, mechanoreceptor. Chemical makeup, chemoreceptors, special chemoreceptors, right? Proprioception, mechanoreceptors. Gustation is done by chemoreception, right? There's actually specific chemicals, tastants are chemical molecules, and they bond to ligand-gated chemoreceptors, and they open up when that bitter, salty, sweet, salty, and umami, right? Temperature is done by thermoreceptors, very special proteins and receptors that change shape. They shrink and swell like a lot of things, like everything does. Everything shrinks or swells under different temperatures. Those membrane proteins shrink or swell, and that allows for a channel to open or close. Olfaction is a chemoreceptor, done just like gustation. And blood osmolarity is done via an osmoreceptor. All right, simple to the point. Thanks for getting this queued up, and we'll head now into a little bit more detail on the specific somatic sensations and some of the specific receptors and a little bit more detail on adaptation. So thank you very much for watching, and I hope that helped.